Hello my dear students, welcome to my channel, and in today's class we will do refraction through prism. Now refraction through prism, in this topic we will try to discuss what is meant by prism and what are the terminology that will be going to use in this topic of prism will also be discussed. And this prism is a transparent medium which is capable of producing dispersion of white light into its constituent 7 colors. Okay, so let's try to jump into the topic and let's see what we can learn from it. The first one is the definition of prism. What is prism? Prism is nothing but this is a transparent medium, okay, and it is also a wedge shape, okay, and it is bounded by two refracting plane faces inclined to each other at a certain angle known as angle of prism. So you can define a prism in a very simple way, that this is a transparent medium. Any transparent medium, it may be glass, it may be water, whatsoever. If it is transparent, then you can take it. So it is a transparent medium bounded by two plane refracting faces, okay, inclined at an angle known as angle of prism. That transparent medium, we call it as prism. Now you might have seen prism in your laboratory also, and you may want to say that, sir, this prism is not only bounded by only two surfaces. On top you will see a triangular, okay, surface, and on the bottom also a triangular base is there, and the other three sides are just like a rectangular plane faces. But my dear, I'm telling you that this, I'm not saying that it is bounded by all those surfaces, but I'm telling you only two, okay, what plane surface. If a transparent medium having only two plane surface inclined to each other making an angle, then that type of the transparent medium, we call it as what, prism. Let's try to see the actual, okay, diagram or picture of this prism, and I will tell you what is as per the definition as I have given you about the prism. Okay, now let's see, this is a prism, okay, and these two, it is shown there with the refracting faces there, here, okay, and here like this. This is nothing but this is the refracting plane surfaces, okay. Now you may say that there one rectangular, one triangular face is also there, and there it will be also one triangular bottom may be also there, like this, somewhere here like this, okay. So there are many faces, and this will be rectangular faces, one rectangular faces there, and on the other side also there will be one rectangular face there. I'm not saying all those surfaces, okay. What I'm trying to say is that this is bounded by two plane what surfaces inclined to each other making an angle. Suppose if we take it these two as the refracting, this one, no, I will not do it like that, rather I will do like this. Suppose this is one of the plane refracting face, and this is also one of the plane refracting faces, okay. If a light ray passes through here, and then it will pass through here like this, and then it will be emerging out here like this. This is the incident ray, refracted ray, and the last one will be the emergent ray. Now when we take it like this, the other rectangular surface which is not seen, okay, that means onto the other side, okay, of the screen, that rectangular face is not taking part in the refraction. So when we define prism, we define only with these two what rectangular faces, this face and this face, okay. So what is that? A prism is what? Is a transparent medium bounded by two refracting faces inclined to each other making an angle known as what? Angle of prism. Where is that angle of prism then? If these two are the plane refracting faces, okay, which takes part in that refraction, then what happen? Angle of prism means this angle, these two plane faces inclined to each other making an angle where? Here, right? So this angle we call it as angle of prism and denoted by capital A. Now let's see. So this is the angle of prism. When I draw it, then it was somewhat misplaced, okay, but A should be, as I told you, that this A should be somewhere here in between these two plane faces, okay, but I made it here, just there is a mistake. So now let's see, when the light ray passes through, then what happened, let's see. So this is the part of the ray that will take what this refraction through these plane faces, okay. Now we will see another type of that of what the cross-sectional view of the formation of this refraction of light through this prism. Now let's take it that ABC is a prism, okay. We are seeing only the cross section, okay. Now the refracting faces AB and AC are the two refracting faces and which are inclined, okay, with an angle, and it is denoted by the A itself, okay. The point or the vertex is also denoted by A, and the angle of the prism is also denoted by A itself, okay. And this triangular that is shown here, ABC, it is a prism, and of whose refracting what index, okay, refractive index is denoted by what, mu. Now let's take it that a light ray is passed, or white light is passed through this what surface AB like this, and it will be refracted here and it will emerge out, okay. So we call it this light ray as the incident ray, the refracted ray, and the emergent ray. Got it? So the first one is what, the incident ray, the refracted ray, and when it comes back again in the same air medium, then we call it that ray as the emergent ray. Got it? Let's take it that these are the normal at the point of what, incidence, okay. This is the point of incidence and this is point of emergence, okay. So what will be the angle of incidence between the incident ray and the normal? We call it that as what, angle of incidence, okay. And that of the angle of between what, the normal and the refracted ray, we call it that as angle of refraction. And another angle somewhere here, the angle here, okay, that angle between the normal and the emergent ray, we call it that as angle of emergence. This we call it as angle of incidence. The refracted ray and the normal, we call it this angle as angle of refraction. This also we will call it as angle of refraction, R2, denoted by R2, okay. And suppose this is the incident ray, the direction of the incident ray will be like this. So the angle between the emergent ray and the direction of the incident ray, this angle we call it as angle of deviation, and it is denoted by del or D, okay. It is just like a D, but not D actually, but it is denoted by del. You can also denote it by D, small d also, no doubt, English letter small d, but it is not just small d, but it is just like a del like this, okay. This is a Greek letter, not English letter, right? So let's see as it is given here, okay. Now this angle I, you will see I there, and angle E, angle of incidence, and angle of emergence, and the angle of refractions, okay, R1 here, angle between the refracted ray and the normal, and the other also the refracted ray, which will be the incident ray for the refraction from this what, refractive index mu, okay, from the prism to the air. For this, what happened, your R2 will be the angle of incidence, and your angle E, which is angle of emergence, will be now taken as what, the angle of refraction. I'm talking about somewhere here, okay, refraction from the prism to air. So if this is the normal, okay, this line, I mean, this will be taken as the incident ray and this will be taken as the refracted ray. Got it? Yes. Now let's see about that of angle of deviation, okay. Yes, like this. So this, the angle between the emergent ray and the incident ray, we call it that as angle of deviation, and it is denoted by del there. So there is a relation between this angle of incidence angle of incidence, okay, angle of emergence, angle of deviation, angle of prism, okay. the these four variables, okay, angle of incidence, angle of prism, angle of deviation, angle of emergence, the relation, okay, or the expression relating these four quantity, we call it that as what? Prism equation. Okay, just like in the case of lens, in the case of mirror, you are having mirror formula, lens formula. Okay, you can also say that this is prism formula, you can say. So what is that prism formula? The angle of incidence, okay, plus the angle of emergence will be equal to angle of prism plus angle of what? Deviation. Or you can state like this: the sum of the angle of incidence and the angle of emergence is equal to the sum of the angle of prism and the angle of deviation. Got it? This formula we call it as what? Prism formula, right? Now let's see for the next what we can learn from it. Now let's take it that this angle of deviation, on what factor this angle of deviation depends on. Let's see. This angle of deviation depends on angle of prism, no doubt, angle of incidence, then the material of the prism and the wavelength of the light that is used. Okay, that wavelength of light that is used means the wavelength of the incident light, I mean. So these are all the factors that is what giving you the different values of deviation. So angle of this angle of deviation depends on what? The angle of incidence, the material of the prism, that means the refractive index of that prism. Okay, material of the prism, we call it that as material of the prism simply, and the wavelength of the light of the incident light. Okay, the wavelength of the incident light used, that is also depending on this wavelength. It also varies the angle of deviation and also the angle of prism. In most of the prism that we are having in our laboratory, this is that are nothing but that are equilateral prism. Why? Because the angle between this angle of prism, these are all 60 degree. Okay, so there are others also having what 45 and 90. That means one angle will be 90 degree and the other two will be having what this 45 each. So we call them as right isosceles equilateral prism. Okay, like that. So let's see now about the dispersion, okay, of white light through this prism. While we define prism, we can define prism as a transparent medium bounded by two plane faces inclined to each other, making an angle known as angle of prism. And you can also define that and capable of producing what? Dispersion of white light into its constituent 7 colors. You can add this also. Okay, that transparent medium is known as what prism. So this prism can split, okay, this white light into its constituent 7 colors. Okay, and this phenomenon of splitting of white light into its constituent 7 colors, we call it that phenomenon as dispersion. Okay, so dispersion is a phenomenon of what? Splitting of white light into its constituent 7 colors. Okay, and if these patches of 7 colors if obtained on the screen, then we call it that patches of colors obtained on the screen due to dispersion, we call it that as what? Spectrum. Got it? We call it that as spectrum. So spectrum, in order to remember it, those 7 colors, okay, then you can remember this big year: V for violet, I for indigo, B for blue, Z for green, Y for yellow, O for orange, and R for red, like that. So you can remember this big year, and then you can easily remember the order of the color. Okay, so we will try to see about this dispersion of white light in the actual way. So now let's see it. Now you take it this as a prism A, B, C, D. A is missing there, but take it for granted that somewhere there A is there. Okay, so A is there. Now let's see that white light is incident onto it, and okay, what it will happen. Let's see. So let's take it as screen like this. white light is incident on it, and you will see that the white light, okay, is splitted through refraction of white light through this prism. It's splitted up and it emerges out as a different colors, starting from that violet, then it goes to like this, that of to the red, violet, indigo, blue, green, yellow, orange, red, like that. Okay, so it will be like that. Now when we see like this here, the incident, okay, ray, it will be in this direction like this. Okay, so now you will see that if there is a normal here, then the angle of refraction between the refracted ray and the normal, for all these colors, it will have different angle of refraction. Your angle of incidence will remain same for all those colors. You may take that this here white light means it consists of that of these 7, okay, different colors, okay, like this, got it, or red at the last, got it. Now see what happened, all those 7 colors will have the same angle of incidence, but for different colors, okay, different colors have different wavelength. So for violet, the angle of refraction is less, and for that of red, it is the largest, right? Got it. But this angle of deviation, for this red light, the angle of deviation is less, and for that of the violet, okay, it will be from here, not up to here, it should be in this angle. I mean, if you retrace backward, okay, this will be the deviation for violet. So violet is deviating what, maximum, and your red light is deviating less. That means the bending is less in the case of red light, and bending of the violet light is what, maximum. That means from this incident direction, bending is less for red light, but bending for that of violet is what, the largest. Okay, bending means from here how much it has been bended. For red light it is less, and for that of the violet it is bended most. Okay, so we will learn about that in the case of this, of what we call it as refractive index. We need to recall that second law of refraction known as Snell's law. Okay, there you will find that refractive index. Okay, this is equal to sine of angle of incidence to the sine of angle of refraction, like that, no? So from there we will try to also explain this, what causes of what, this what, this distribution or splitting of white light. Okay, now let's see step by steps. Okay, so this is the actual direction of the incident ray, and the red light is retraced backward, meeting with that of the actual incident ray direction, and is intersected at the point D. Likewise for the what violet we will also do, and this angle is denoted by del R for that of the deviation of red light. For the violet light, it is denoted by del V. Okay, when you compare with this del R and del V, del R is less than del V. Okay, that means deviation for red light is less than that of deviation of the violet light. Okay, this is a normal, and angle A is also coming up there. Okay, now let's see what are the, okay, how this splitting takes place. Let's see, this is a white light and incident onto the prism. Then what next? Okay, what will happen next? We will see that we have already seen that in the previous slide, that when white light is incident, or white ray is incident onto the prism, then the white light splits up and it refracted at different angles. Okay, that will be just like this, and it will be emerging out, and whatever it is obtained onto the screen, we call it that different patches of color as spectrum. Okay, so red is deviated most or less. Yes, I've told you that red is deviated what, less. Okay, and next is what, whether that violet light is deviated more or less. Violet here at this here, it is what, deviated maximum. Okay, so it will be what? Deviated most, and this is the spectrum that will be obtained onto the screen. Okay, starting from the upper side red to the lower side onto the screen of that of violet. Okay, so these are the red, orange, yellow, green, blue, indigo, and violet. Okay, actually while I'm making it, there is some small mistakes is there. Okay, now this part will be red, this part will be orange, and somewhere up to here it will be orange, and this will be for yellow. This region, I mean, this region will be for red, this region will be for orange, this region will be for green. Okay, up to somewhere here, then it will come then blue, okay, then indigo, then to violet, like that. Okay, so here will be what? Violet, indigo, blue, then green, then yellow, then orange, then red. It will come like that. Okay, in that manner, right? Now let's see about the causes of this splitting, or rather the dispersion of this white light into its 7 constituents, different colors. Okay, we call it this relation as Cauchy's relations. The refractive index of that material of the prism mu is equal to A plus B divided by lambda square plus C divided by lambda to the power 4. We call it these as Cauchy's relations, where A, B, C, these are nothing but these are the constant for that particular transparent medium. Now if these A, B, C are constant, then we can say that this mu is what? Inversely proportional to what? 1 by lambda square. Now this lambda, if this lambda keeps on increasing, okay, lambda to the power 4, then this quantity will be very, very small, and we can neglect it, and we can say to some fair approximation that your refractive index mu is inversely proportional to the square of the wavelength of the incident light. Now in that white light there are 7 colors, and those 7 colors will have different wavelengths. Okay, violet will be having a definite wavelength which is different from that of indigo, okay, or which is different from all other colors. So just like you also have your own name, your own roll number in a particular session, likewise these different colors will also have different wavelength. Your roll number in a particular session is your characteristic, okay, of you yourself. If a particular boy, say suppose Tom, is having a roll number 5, then in that particular session in class 10A, if I said that Tom means what? He will be having that roll number 5, or 10A roll number 5 means what? It will give you that particular boy Tom and none other. Likewise, if you are having a particular wavelength of light, then that particular wavelength of light is nothing but that is the characteristic feature of that particular light, which will give you a different color, okay, a definite color I should say. So what happened? I told you that at the time of that of Snell's law, while doing your laws of refraction, these laws of refraction, what we call it as refractive index. What is this significance of this refractive index? Mu. This refractive index will give you nothing but this will give you the degree of banding. Okay, how much the refracted ray will be banded from its actual direction of the incident ray. That will give you by this refractive index mu. So what happened? This degree of banding, then it depends on what? It depends on this wavelength of light. Okay, forget about that square and all. You just take it that your mu, okay, it is inversely proportional to the wavelength. We can also simply say like this, okay, for the explanation, right? Then when we come to know that this refractive index is inversely proportional to the wavelength, we also know that your red light is having what? This maximum wavelength, and your violet is having least. Okay, violet is having least wavelength. That means wavelength of violet is very, very less than that of wavelength of red, we can say. Got it? if red is having the highest wavelength, then what happened, I told you that your mu is inversely proportional to this wavelength. So what happened, highest wavelength means what, you will have your refractive index for red color that will be least, okay, and the smallest wavelength of violet, that will be having what, your banding, okay, your refractive index, okay, of the banding of the white light will be maximum and that of red light will be least. So your banding comes from where? Comes from this relation, Cauchy's relations. What does it says? That your refractive index, that means banding of the light, it depends upon the wavelength of the light. Okay, in the actual relation it should be like this, 1 by lambda square, where a, small b, small c, these are constants for that particular material of that transparent medium of the prism, right? So when one asks you what is the cause of dispersion, you can say that it is due to the Cauchy's relations, which gives the relation between what, your refractive index of the medium with that of the wavelength. And you can also say that your mu is what, your mu is equal to what, constant divided by lambda square, or you can simply say that your mu, okay, is inversely proportional to the square of the wavelength. You can also say like this. Let's see another expression also. You can also express it in terms of what, in terms of the angle of refraction also. We know that from Snell's law, okay, we know that from Snell's law that mu v is equal to sine of I divided by sine RV. I told you that this sine I will be constant for all the colors. Okay, let's take it for violet. For violet, what happen if you take it this as RV, then what happen, as per your Snell's law, your mu v, okay, will be equal to sine I by sine RV. Okay, for a particular violet ray, okay, your RV will be here as it is written here, RV, okay, but this I will be constant. For the next for red light, it will be also sine I by sine RR. RR means this is the angle for that of the angle of refraction for that of red light. Okay, now then when we compare it this, okay, this angle of incidence for the violet light is lesser than that of angle of refraction for the red light. For violet is this much and for that of red light is this much. So angle of refraction for that of red light is more. So what happened, your refractive index for red light and for that of this red color, okay, the angle of refraction, I mean, they are inversely proportional. Got it? More the angle of refraction, what happened, this more means what, the hole will be less, so banding will be less in the case of red light. Can you get my point? So more angle of refraction, if you divide it 20 divided by a big quantity, then this will be small. If you divide this 20 by a small quantity like that, then that quotient will be very large, right? No? So what happens if your angle of refraction for red color is very large, then what happens, this mu r will be what, less. That is what we are getting here. But for that of violet light, for that of violet light, your RV is very small. If you divide it by a small quantity here like this, then what happened, the quotient will be very large, so your mu v will be very large. So that is why the banding is very large in the case of violet, but in the case of red light it is very small. Got it? So that can be also the explanation for the causes of dispersion also. The refraction, okay, for different colors, the angle of refraction for different colors will be different, okay, and so it gives the causes of dispersion also. That is also given here. Okay, you pause the video and you can note it down it if you want it. Okay, now let's see those different things between the red and violet light. As I told you that red light is having the longest wavelength than that of violet. For that of violet light, it is only that of 400 nanometer, I mean the wavelength. the distance between any two consecutive crests, we call it that as wavelength. Okay, this one or this one doesn't matter. Between any two consecutive, you cannot take it this one and this one because you have jumped one crest here. So it should be in between any two consecutive wave or crest. I mean, the distance between any two consecutive crests, we call it that as wavelength. This will be all wavelength. Okay, so when you compare with that of red light, what happened? The red light is having what more wavelength than that of the violet light. So your violet light is having wavelength of 400 nanometer, whereas your red light is having that of wavelength of 700 nanometer. Okay, so 700 nanometer is more than that of 400 nanometer. So wavelength of red light is more than that of violet light. Okay, now that's all for today's class. Thank you for watching my video. Okay.